Okay, let's have a look at resistors in parallel now. So you remember that when resistors are placed in the same loop, then they're described as being in series. Well, in this particular circuit, the resistors aren't in the same loop, they are in different branches of that loop. And then those branches recombine, and we need to complete our circuit. So there's our circuit, and there's it with our battery. And we'll call this R1, resistor 1, and R2. Now, if we wanted to work out the effective resistance of these two resistors, we need to use what's known as the parallel resistance formula. So these resistors are in parallel. Okay. Now the formula that we use is a little bit tricky, but it's not that bad, but it just takes a little bit of getting used to. To work out the total effective resistance, it is 1 over RT, where RT is the total effective resistance of these resistors, and it equals 1 over R1 plus 1 over R2. So it looks a bit unusual. Let's actually do an example so you can see how it works. So let's say that R1 had a resistance of 50 ohms, and let's say that R2 had a resistance of 20 ohms. And what we want to do, we want to work out what is the total effective resistance of this circuit. In other words, these two resistors combined, what total effective resistance will they have that the battery will fill? And once we'd work that out, we could then work out what the current leaving the battery would be if we knew the voltage of our battery. So let's go ahead and do it. So the total effective resistance of these two resistors will be 1 on RT. So RT is the total effective resistance. There it is there, of these two resistors. And it's going to equal 1 on R1, which is 1 on 50, plus 1 on R2, so it's 1 on 20. Now, there's a totally accurate way of doing this and an approximation way of doing this. We would like you to actually use the really accurate way, which means using fractions. Now, if we're going to add fractions together like this, we need to give them the same denominator, a common denominator. Now, the lowest common denominator for both of these fractions would be 1/100ths. So I could convert 1/50ths to 2 100ths, and I could convert 1/20th to 5 100ths. Okay, so therefore 1 on RT will equal 2 100ths plus 5 100ths, which is 2 plus 5 all over 100, which is 7 over 100. Now remember, that's 1 on RT, so 1 on RT equals 7 over 100, but we actually want RT, so I need to flip that fraction and that fraction upside down. So we've got RT over 1 equals 100 over 7, or RT equals 100 over 7. Now, that is the exact resistance, or the exact effective resistance of those two resistors. Of course, in a exam style problem or a practical problem, you'd actually want to work that out as a decimal, and so 100 divided by 7 would be, let's see, it'd be about 12, what's that, 14, 13? Let me just quickly work that out. So 100 divided by 7 is 14.29, okay? So that'd be 14.29 ohms. That's interesting. Look at that value, 14.29 ohms. We've got a 50 ohm resistor and we've got a 20 ohm resistor, but when they're placed in parallel, the total effect of those two resistors in this circuit gives us a total resistance of 14.29, and that's lower than even the 20 ohm resistor. And that's actually something that will always happen when you've got a whole lot of resistors in parallel. The total effective resistance of that parallel group will be less than the lowest resistor in that arrangement.